her PhD, Priyanka obtained an undergraduate degree from IIT Madras in India and was a visiting scholar in Leibniz University in Hanover, Germany. She has published several papers on continuum robots during her PhD. Today, she will present part of her work. And yeah, we are all excited to hear from her. Priyanka, the floor is yours. You can start. Thank you.
Can you all hear me okay? Oh, okay.
Yes, it's up.
Okay.
It's up. Yeah.
Yeah, it's good.
All right. Let me share my screen, set up. Yep. All right. Thank you, Farhad, for inviting me, and thanks to all of you for joining in during a lunch break. I appreciate it. I'm a PhD student at the University of Toronto. I'm in my final year, and today I'll be introducing these flexible robots we call continuum robots, and we'll talk about how we can use them to enter cluttered environments through a very small port and use it for various tasks. Oh, okay. Yeah, use for various tasks, and we'll be doing this through the lens of modeling and motion planning. Okay, so we're all familiar with serial manipulators. So you basically have rigid links that can move around, do certain tasks. And now if you have this cluttered environment, which you see these blue circles, the idea is these robots are kind of restricted in their motion because there's not much really that they can do. One solution that you can do is simply add more links. So you have more links, more motors on the robot to navigate through this clutter. But then if you can imagine this, you sacrifice on the slenderness of these robots because you have all these motors on the robot body. And there's not really much you can do. It's akin to like a bull in a china shop, for example. It's not really that easy. So the idea behind continuum robots was, hey, what if we replace these rigid links with flexible ones and have these flexible robots be extrinsically actuated, so the motor is usually placed outside the robot body. What this means is you can make these extremely slender, so they can enter a narrow port. If you have a cluttered environment, they can kind of snake their way to do particular task at whatever the user determines what this looks like. And because of this property, they can be scaled down to very small levels. So they're used for minimally invasive surgery, or you can make them slightly longer and use them for inspection tasks in jet engines or turbine blades. Okay, so we have this. If you look at the motion, if you look at a prototype that's moving here, you see how slender and thin it is and how compliant. And if you want to design such a robot, what we do is we have tendons running parallel to the robot backbone. And by pulling or releasing these tendons, the robot then deforms to take curvilinear shapes in space. So if you want to design this robot for this sample cluttered environment, we have to look at what this is made of. So this video here is made of 3 links, or what we call segments. And this segment, if you look at its motion, the simplest case, it bends in quite a simple way. And if you wanted to navigate something so complex, we end up having, and that's what's commonly done in literature, you end up having to stack multiple links on top of each other because each link is kind of limited in what it can do. And then you run into the same problem as before, because if you look at the actuation system for the video we see on the left side, you can see how small the robot is. Well, the actuation system is quite large because you need at least one motor to actuate 1 or 2 tendons. This adds up pretty quickly. If I wanted to have multiple such links stacked on top of each other, you can see the actuation system, both the design and the control, can get quite complex. Okay, so we have this setup. It's complicated and we're running into the same problem. What's something that we can do? One approach is to move away from this simple tendon routing I mentioned before. So what if we change the tendon routing, for example, a helical pattern or a sinusoidal pattern, and then use that to change the shape that the robot takes. So each link now has a more complex shape it can take. Another approach that I've also worked on is, let's say we add something we call locking mechanisms. The idea is this locking mechanism here constricts the shape of one half of the link or segment such that the other half is free to bend however it pleases, such that you get this more complex shape. But Doing this is not without its challenges. As you can imagine, if we add more complex actuation, again, we run into the same problem. We need additional motors to have to actuate this changed tendon, or we need, for example, in this video, we used an external magnetic field to control this locking mechanism. But what we wanted to do was look back at why we started looking into these flexible robots and say, okay, what can we do differently? Because the idea behind these robots is moving away from the traditional paradigm of having these rigid links, we said, okay, usually with these serial link robots, we shy away from contacts. We don't want the environment to get damaged. But now we have these flexible robots, yeah, which can have these more softer interactions with the environment. So why not make use of it to have contact data navigation? The idea is that the robot essentially doesn't shy away from making contacts with this environment and potentially uses it to kind of snake its way through the environment and look around and do whatever task it's supposed to. So at the most fundamental level, if we want this to work, what we need is a motion planner. And this motion planner needs to autonomously guide the robot to a target position or a target pose through this clutter. And it needs to do this without the user telling it what contacts it needs to have, but the motion planner itself infers what is the, am I blocking your view?
Oh,
sorry, okay. With the motion planner kind of telling it autonomously what sequence of contacts it needs to have. So if you look at the problem definition, because that's what researchers like to do, we like to define our problem and the scope as well. We have a single link, a single segment robot. The joint values for this robot are the, I'll explain a little bit, but basically it's the tendon, the segment length that's inside the workspace, because 1 degree of freedom comes from inserting it and retracting it from the workspace. And the second one, which is L tendon, basically tells you how much you need to pull or release your tendon to bend it. So you have your second degree of freedom that allows you to move. So the goal of this motion planner then is, given this input known environment, it needs to spit out a motion plan, which is a sequence of joint values that it needs to go through in order to reach our target. And this target is considered a success if the tip ends up reaching this target pose within a certain tolerance. And what it needs to do throughout the whole process is interface with a model. This model basically simulates how the robot bends to these actuation inputs, as well as takes into account what the contact interactions, how the contact interactions affect its shape. So there's a whole lot of literature over the last decade on how to model these robots, because if you can imagine, it is not as straightforward as maybe DH parameters or just writing it out with geometry, because you have all these complex forces, contact interactions, tendon forces coming into play. So I've linked one of like a literature review we did surveying all these papers. But the main key takeaway that I want you to take away from this is this model is highly nonlinear. It is not straightforward to solve. So given that we have this complex model that doesn't come cheap, how do we go about doing this? One of the first challenges we faced was realizing that when you have contact interactions, your joint values don't have a one-on-one mapping to the robot shape. What this means is, let's say I do 3 length insertions and 2 bending versus 2 bending actions and 3 length insertions. You see that the joint values are the same in value, numerical value, but the robot shape now is completely different because these contacts remove whatever one-on-one mapping we began with. So what this means is there's no direct inverse kinematic solution that I can just plug in and say, hey, just spit out all possible robot shape and what Q goals look like. Usually in traditional robotic motion planning, we know what Q goal looks like. We know what Q initial looks like. And a lot of the planning is just figuring out what the intermediate Qs look like. But we now don't know what this Q goal looks like. And what this means is we need to search through different joint space sequences rather than joint space values. And when we do this, each node or each state needs to be represented not just by the joint value, but also for now we uniquely identify it by a vector kappa, which basically, if you can imagine, this curve is represented by a sequence of m curvatures. Okay, So now we know we need to explore this state space. We can build a tree. We can start from the initial joint value. We can have a okay, I have shared my screen. I panicked for a bit. Okay, we have started from the initial Q value. We go up to, let's say, Qi. We can apply four sequences, insertion, retraction, bending on the left, bending on the right, to produce these children nodes that we know now have different shapes. And we can then keep expanding each of these nodes. That's well and good. But as you saw, every time we do this, we need to run a full model, which is computationally expensive. What we could do instead is we decided to come up with a crude model, which we call a crude model. Basically, this model approximates the robot mechanics because we don't really need the exact value each time. We can afford to have a little leeway in what we do. So we do something called a look ahead search. So we have, let's say we have a node that we've run the full model. We know exactly where the robot tip lies. We can expand its children, not with a full model, but we can run this crude model to approximate the end effect, the robot shape. And then we can sequentially expand it for, let's say, 5 levels of this tree, and then run the full model so that we don't accumulate too much error over the process. Again, this is nice. We've solved one of our computational issues. But then if we do a simple breadth first search through this tree, again, you can imagine it is computationally expensive if I go through each node and then look at its children and then its children. And what I need instead is a heuristic, which you might be again familiar with in the motion planning community. Basically, the heuristic guides the search. It tells the planner, these are nodes that lead you closer to the goal. So spend time or effort in expanding these nodes instead of looking at all other nodes that might not necessarily lead you to the final goal. Okay, so now we have these three components. Over the next couple of slides, I'll talk a little bit about what this crude model that I spoke about looks like. Then I'll talk about the heuristic that we devised to do so. If we look at the full model, or the actual model we use to represent these robots, what we do is we take a link or a segment, what we call a segment. We say that this segment can be divided into a series of sublinks, and each of these sublinks can be modeled as a constant curvature arc, which has one curvature parameter to represent it, or 3 in 3D. If you write the moment balance for each such sublink, you can sum up all the contacts from gravity, contact forces, tendon tensions, etc. And you can equate it to the internal moment that each sublink experiences using the Hooke's law. So you can say, okay, these are the moments that are acting on the sublink, these are the internal strains, what are the resulting curvature parameters. So what this model now does is it takes your input forces, splits or input joint values, calculates what the vector of curvatures looks like, so kappa, which is our m-sized vector. And then once you know what the curvatures look like of these constant curvature arcs, you can easily calculate what the vector t, or the robot tip pose, looks like using geometry.
Sorry, TDCR, what does it stand for?
Oh, sorry, Tendon-Driven Continuum Robot. So just continuum robots that I've been talking about. My apologies. Yeah. Sometimes we just get so used to the short forms. I see them all the time. Not spotted, but thank you. Yeah. Sorry, Mom. Yeah, basically it's just the robot model. It's nothing else. Sorry, yeah, okay. So now we know we have this model. It solves nonlinear equations. Each time I need to solve the motion planner asks to expand a set of joint values. So if we look, so we asked ourselves, okay, we have m nonlinear equations. Can we simplify this, reduce the system to a simpler state so that we don't have to expend this much computation energy each time? If you look at what are the configurations that come into play when you're doing contact implicit motion, there are two kinds. The first is contact free. You basically don't have any contact. It's a free moving robot, which is more common. The other is a in contact configuration where the robot is undergoing these interactions with the obstacles. So for both these configurations, we can identify contact free portions. So you basically have these, you can divide the whole robot into parts. These portions, parts where you don't have any contact force, you can call them contact free. It's easy, we know there are no external forces acting on it, it's good. The other parts where there are contact forces acting on it can be divided into in contact portions And each of these portions, if you can see, has a force acting at the tip, and this force corresponds to the contact force that your environment applies on the robot. So then, are there approximated backbone parameterizations in literature we can use to reduce our computation time? So what in our literature review, we studied, okay, there are these different representations. We won't worry about what they look like, except for this one, the one marked in green, which we see is like quite fast. What is this like CC model? I'll get to it in the next slide. So the idea is what a lot of literature covers is they model the entire link, this flexible link, as a constant curvature arc. So you just have one parameter instead of the m parameters I mentioned earlier. The whole thing is just one curvature. And you can use this to represent like in-plane bending. And what this means is it cannot account for these external forces. So if I can recall quickly, we have these contact-free portions that don't have forces. And these constant curvature representation works well for them. It's fine, we don't have any forces acting on these portions. We can directly use them to represent these structures. But for the in-contact portions, there's not really much we can do. We cannot use this representation to represent the in-contact portions. But nonetheless, we know it's fast, it's cheap, people like it. It's one of the most commonly used representations because nobody wants to solve nonlinear equations that does not run in real time. So we said, okay, what's the next best thing we can do to represent these external forces acting at the tip? What if we, instead of the constant curvature, we took something called an Euler curve or a linear curvature representation? The idea is, instead of just one curvature parameter, you linearize the curvature along the backbone, so you have two. And with this, you can not just represent the moment acting on the body, but also an external force. And we took inspiration from the computer graphics community. We said, okay, what if instead of just solving all the Fresnel integrals to figure out what the robot shape looks like, what if we divided it into a series of constant curvature arcs as before? But instead of having m curvature parameters, we force these the curvatures of these arcs to be in arithmetic progression. So what this means is you have two parameters per portion or with the force acting on this part. And with this, you can represent the entire robot shape. Any questions so far? Am I running through? No? Okay, good. Okay. So we need to investigate how accurate something like this would look like. So we proposed a model that can model this external force with just these two parameters. And we saw that the accuracy of this model was comparable to other models in literature. But what we are interested in is the computation time. So this is a logarithmic plot. On the y-axis, you see the computation time in milliseconds. And we see that the Euler arc span, which I call EAS here, outperforms these two other common models in literature. It's almost 4 or 5 times faster. So, okay, we know now that we've validated that this representation is fairly accurate if we have these external forces acting on the robot. So we plugged it back in. We looked back at the possible contact configurations we can have. For the free portion, we know we can use the constant curvature arc, so one parameter. For the in-contact portions, let's say you have k number of contacts, you basically need k Euler arc splines to represent it, plus, so that's 2k parameters, and then one parameter from the constant curvature portion that's just free moving and doesn't really experience any external force. So the idea is now you have a system that's simpler than solving all nonlinear equations, and we studied how much faster this would help our search. So basically, if we compare the distribution of the full model versus the crude model that I proposed right now, we see that there's almost a 2.5x improvement in computation time. And the computation times here, as you can see, are no longer in milliseconds, it's in seconds, because now, if you can imagine, the robot has to undergo way more complex interactions with the environment versus the simpler tip force that I only looked at last time. Okay, so now we have a crude model, which was one of the second objectives we set out to solve. Now we need a heuristic to guide the search. So a heuristic, if you can think of it, is simply a cost to go. It tells me how far I am from my target. So if I wanted to reach, let's say, just a target position, that red dot you see on the right, the heuristic is fairly straightforward. What you can just do is you can take the heuristic to be, let's say, the Euclidean distance to the target, or you can say you can do some kind of wavefront planner from the target such that you know exactly how far the robot tip is from the target. And then you can tell your search, hey, just expand nodes that lead to a lower value of this heuristic, and that way we should be good to go. And this works very well because you can approximate the robot to just by its tip. You just expand nodes that take the tip closer to its goal. But let's say we wanted to reach a pose instead. So you add an additional layer of complexity here. One common way to design a heuristic for such a scenario is to use something I'm going to refer to as H simple. Basically, it's a weighted sum of this shortest Euclidean path we saw earlier, plus an angular difference between the current tip orientation of the robot and the target pose. And usually the idea is robots have an additional degree of freedom that you can use to control its pose. So as you get closer to your target, you can simply change your robot orientation to reach it. But our system is underactuated. That means that there is no control input. As you can see, that I can just apply to this robot to make it change its orientation. And the only way this happens is if there's an obstacle that this robot is leveraging against. So in some ways, you can think of this obstacle as a passive control factor that you can think of the obstacle as a passive control that allows the robot to change its orientation.
Just to understand,
Hmm?
you can only change the curvature at the root of the snake, or can you change it anywhere along it?
Yeah, you cannot change it anywhere along it. So you basically only have control at the base. So whatever you apply, the one control, the whole robot shape is going to be affected by it. And that's why you see there's like simple bending. So if you wanted to do additional local control, you would have to add like additional tendons or additional actuation to change it just locally. Yeah.
Does this also mean for some scenarios, like you might not be able to find a solution?
Yes, it does. So what this means is you cannot just randomly sample targets and assume that the robot will be able to reach all of them, definitely. If you want to do this, adding an additional degree of freedom would be the way to go. But the idea is, if you had something like this, there are a lot of cases where you want to orient the robot in a certain way. So if you have another robot coming in to support it, if you have other tasks, for example, if you have a camera, it's much easier. And this is only, okay, maybe I'm getting ahead of myself, but another application that I think would be very interesting is using these obstacles to change the stiffness of the robot. Not just, even if orientation is not that important. If you can imagine, it's fairly compliant, which is good. It helps us get where we want. But once we get there, maybe we want to do a task that requires the robot to be more stiff. So it could potentially use this obstacle as a support to do this task. Okay. Does that answer your question?
Yeah.
Yeah.
And also the location.
Yeah.
So this planning problem, so we know the locations of the obstacles in advance.
Yeah.
Okay.
So we started from the simplest case because that's always the first step, right, to building. But potentially, and I'm going to get to it eventually, but I mean, I think there could be a potential future task is you have an unknown environment, just because this robot is flexible, if you stick some sensors on it, you know where the robot shape is, you could potentially figure out where your obstacles are, kind of map out the environment eventually, because you can use them as proprioceptive sensors. But right now, yes, we know the environment, we know that the obstacles are fixed, and we use this to move our robot through the environment. Yeah. Okay, so this heuristic now is not very simple. If you can imagine, for example, parallel parking. For those of you who drive a car, it's non-holonomic. I cannot just change my orientation and just drive where I want. Yeah, I need to figure out a nice steering for me to go around and get to the orientation and position that I want. While this is nice and good, we can adopt this idea for our robots too. What if the end effector was the equivalent of a car, if we can think of it, and say that this end effector now needs to steer in these curves to get where it wants to. So if you look at the heuristic, so this is what, so after like scratching our heads for a while, we came up with this heuristic where we said, hey, what if the heuristic or the distance of the robot towards goal can be defined as a set of these constant curvature arcs? So for this shape here, you can see that it's like constant curvature arc, this is how far I am from the robot shape. But what if you're here, for example? Then you can say that this path is composed of multiple such arcs such that you can make this different turn as you go along. And for something starting from the base, the final path or length to the goal would just be the length of these 4 arcs combined together. And you can say, okay, this is the distance you need to go versus just a Euclidean distance of directly moving to the target position. But the difference here is, in a car, you have a motor on board. So I can change the direction based on the steering I provide to it. But as we discussed, these robots do not have the steering on board. So what we said was, the only place that these arcs can change their steering is when they're closer to an obstacle. So you'll see in both these cases, the arcs only change their curvature when they're next to an obstacle. Now to calculate this somewhat complicated heuristic, where you need to calculate all possible constant curvature paths composed of constant curvature arcs to the goal, what we can do is we can pre-compute it. We can discretize a task space into a grid. Each grid is associated with a pose of the robot tip, and it stores how far this path length is to the goal, such that the path is composed of constant curvature arcs. So we start from the goal, we can compute all the grids that can reach it via this constant curvature arc, store the lengths of these arcs as the heuristic value for these grids. And if we come across an obstacle here, we can identify grid cells that are close to the obstacle. We can identify them as potential contact cells. And from these cells, we can propagate all further like green arcs, or the green arcs that come up here in the second picture. Basically, you only change the direction of steering of the end effector when you are in this contact cell. And we can we can repeat this process throughout until we exhaust all possible contact cells. And we have this grid that stores the path to each part of the goal. Okay, so now we have all components of the motion planner that we set out to complete. We have this nice search, we have a crude model that can approximate the robot mechanics, and we have a heuristic that guides this search. So to evaluate it, we looked at 3 workspaces. They have circular obstacles, either which are convex, placed uniformly or non-uniformly. The non-uniform ones combine to give potentially non-convex shapes. And if you look at the robot motion, we see how it's able to autonomously decide that it needs to bend around certain obstacles a certain way in order to reach the target it needs to go to. Then we also evaluated over about 525 searches, and we compared it with 2 baselines. One is a contactless motion planner, where we said, hey, don't look at contacts, avoid expanding nodes that have contacts. And the second one is using the simple heuristic that I introduced earlier. And we see that with all the setup that we have so far and the proposed heuristic, the motion planner is able to successfully reach its target with about 80% success rate. We also compared the number of nodes expanded by a search, marked in purple on this bar plot, to the number of nodes we would have had to expand if we did a breadth first search. And we see that it's almost 1/20th of the total number of nodes, showing that the heuristic is a nice way, or is effective in capturing how far you are from the goal. And finally, we plugged our crude model back into like a look ahead search, where we only expanded a certain nodes to the full model. And we saw that the computation time as well decreases, because you're no longer spending all your computational effort into expanding all these nodes and running the model.
Good question. The heuristic search, how long does that take relative to the search time?
The heuristic to calculate the
Computing all the
Oh, it is computationally expensive, but the idea is you pre-compute it before a search, so in case you need to do real time, you can just have a lookup table.
Yeah, but
But-
if you don't know the environment, then
Oh, definitely. I think yeah, I think if you didn't know the environment, you would have to use the model as some, like, you need to trust the model quite well and say, hey, if this is the shape of my robot, these are where the forces are likely coming from, and use that to infer back to where your obstacles are. But definitely, good point. Yeah. Another approach could be you start out assuming there are no obstacles. As your robot goes along and you see there's deviation, you add one obstacle, change the way your heuristic is computed, add another, as the robot moves along, finds another one, update your heuristic. And I think, okay, right now, my implementation, I think, is computationally expensive because I didn't worry too much since it's pre-computed. But given that it's just constant curvature arcs, they're very cheap to compute because like, it's a closed form analytic solution, what the robot like curve looks like. So I'm very sure that this can be streamlined to decrease the computation time of calculating all such parts eventually, because it's just matrix multiplication at the end of the day. Most of the, and I also like to add that most of the computational effort goes in identifying contact cells. So we have a curve, we have obstacles. How do you just recognize if this curve is intersecting the obstacle? Is it close enough to an obstacle such that you can identify another contact cell and so on? I think while I personally didn't look into it, I'm sure these are all things in the computer graphics community, for example, that there's a lot of work done in like obstacle collision detection and stuff. So I think it can be streamlined. Does that answer your question?
yeah.
Right. Okay. So during the course of my PhD, there have been a handful of work that look at contact-aided navigation, but sorry, I don't see my screen. Yeah, the ones on the left require a user input trajectory such that the user guides the robot through this workspace to reach a particular task. Or the ones on the right, for example, have a much simpler contact model. They assume that the robot either moves in lines or that the obstacles are just points such that you can find an analytic solution, and then they just sample the entire workspace to find a solution. But our work, I think, is novel in such, our work is novel in the fact that this motion planner is autonomously able to decide what these contacts look like. We have this heuristic that can account for the fact that the robot is under-actuated, there's not a lot of control inputs we can control and instead have to use the obstacles. And we also have this nice crude model that's a nice add-on that speeds up the whole search. And this is what I was initially talking about. I think what I have done or looked into over these couple of slides is only scratching the tip of the surface of what can be done with these robots. Potentially, like you said, you could have these robots go into an unknown environment. Because you're not scared of damaging the robot or the environment, they could potentially have interactions, use it to deconstruct this unknown environment, using this flexible robot as like a proprioceptive sensor. Or, like I mentioned, we can use them for stiffness modulation. We can have them enter like a constructed environment to do a particular task or assembly at the desired location. Yeah, that's it from my end, but I'd love to know more over the next couple of minutes or so, or more about the research at Autodesk. Maybe there's some connections, maybe there's something that you found interesting, not just here, but even people online. Please feel free to reach out. Always happy to discuss research. Thank you.
Yeah, we can open up for questions, both from the room at the office and virtual guests who've joined.
Well, so I have a question about your model. Suppose, can you handle body forces? So, for instance, you have gravity.
Mm-hmm. Yes.
That handle material.
Yes.
Because that's interesting because if you know obstacles, you could potentially use
Exactly. So yeah. So potentially you could. So sorry, for the crude model or for doing this change in curvature?
Well, first you need to model it somehow, right?
Yeah.
And
Yeah. So basically, because you have like a distributed force along the beam, you can think of it as a beam. I like to think of it as a beam. You can approximate that a linear curvature will do the job to model it, but I'm guessing if it's too high, then the linearity then stops failing, you start getting larger errors. But for the size that we work at with like the slender robots, it works really well. So we looked at gravity, we looked at external forces, the linear approximation works quite well.
Can you use it also though as a method of control, extra control over navigation?
I believe we would have been able to if we could control gravity, the value of gravity rather. But I think what could be fun, and this is just of like a drawing board idea, but if you had a mass that you could move along the robot so that you change the way you weight the robot, I think this could be fun and potentially.
Even without that, I could see like if you're just going straight up, then and gravity is coming down, then it's gonna have no influence. But as soon as you go over, it's gonna cause it to curve even more.
Yeah.
In that direction, but then oppose your curve in the other direction.
Yeah. So potentially what we could do if you looked at dynamic, so we look at a lot of quasi-static motion here because we don't want to move too fast. But let's say we're allowed to brake and it's okay, we run something super fast and dynamically, we'd have this fluffy thing, just move fast enough, have it like anchorage over an obstacle and then move and then search the next obstacle it needs to anchor again. Kind of like a snake or a monkey tail, I don't know. But yeah, that's definitely, I think what I've done is just start setting like foundational base, but there's so much I think we could potentially. You have a question?
Yeah, I'm wondering if has anybody looked at using one of these robots to use it as an obstacle to improve how, or if your robot can't reach for some reason, but you could add an obstacle, could you use another of these robots to create that obstacle?
Yes. So potentially, I think that could be the next extension. So my colleague is working on this. So our lab is looking at collaborative robots. So you have two narrow entry ports, and I think this is also used in minimally invasive surgery, for example. You have two narrow entry ports, you come in, you use this robot to kind of support the first one, and then perform these different tasks. And potentially, yes. So now we looked at fixed obstacles, yeah? What if these obstacles could move, but not too much, just enough with friction to give them the little support they need? What if this obstacle was not an obstacle, but like you said, an additional robot that provided the support to allow it to change direction? Yeah, another PhD thesis, perhaps.
Farhad has a question on that.
Yeah, so thank you very much, Prinyanka. My question is about the friction. Have you considered it?
Yes. So, okay, so the crude model itself can handle friction, but when I did the motion planner with the contacts, so let me pull up that slide just to give you an idea of why I made the design choices I did. So if you see here, so this model, just the contact implicit motion does not include friction, but we can use the crude model actually supports friction. In the paper, we actually include gravity, we include friction, and we say, hey, it still works. But here, right now, this model is a much simpler optimization-based model. We just say, hey, I only care about having the robot outside the obstacle. Because if you look at the computation time, it's not real time already. It's, let's say, an average of 0.04 seconds, that's 40 milliseconds, and it takes quite a while, even implemented in C++, to run this model. Potentially, yes, but for the motion planner, we only care about finding a solution, so this worked well. What we could do is use this as an initial guess and just run the friction-based even heavier model than the one I have into this and use that to maybe fine-tune the final trajectory.
Yeah, the computation is something, but the other thing that I don't know if it's true or not, but you can probably tell me. When we have friction and we have multiple contacts, then the friction at the base will be huge. And so my question is that does this affect your final configuration or I don't know, dexterity of your robot, the part that you can reach or not? Like imagine you have 3 points, 3 friction contacts, then I like heuristically, I think that the amount of force in the first contact point will be huge, then the friction will be huge. Then when you want to do any reorientation, you have to apply more forces, then it will be different from what you expected. Like the orientation of or the shape of the robot will be different from what you expected. Is that the right way of thinking of that?
So my pet, so is what you're saying is basically the more contacts you have, the more tension you're going to need to actuate this robot because it gets
Yeah.
stiffer and stiffer. Yes, so that does happen. So in our case, for example, right now maybe it limits to 4 or 5 contacts, but potentially if I had a very long robot and it had maybe even 12, 15 contacts, eventually, yes, I think it would become stiff such that the motor is no longer able to handle the tendon tension. So okay, so does it affect the model for now? For our robot, like it's okay. That doesn't matter too much. For example, like this year we investigated on like a prototype. It worked okay with like standard motors. It's able to push and insert back out from the workspace. Potentially, yes, but I think this would be one of those things that's a feature, not a bug. Because like I said, what you could do is use this to increase the stiffness of the robot and then have it kind of like, because it's compliant, you can use it to circuit through the workspace. And then once you have eventually enough number of contacts, whatever that means, you can make it stiff enough such that it doesn't move. So I think that would be the way to go. Does this answer your question?
Yeah.
Okay.
Can you talk about like your actual build of the robot and how it worked and
Build as in how did I make the prototype?
Yeah.
Oh, okay. So the backbone is made of nitinol. It's a nickel titanium alloy. So it's flexible, it reacts to these external forces. Then we basically 3D printed discs. And right now we glue them, but I'm not a mechanical engineer, so I like to take the nice, easy way out of it. There are ways to get around this, but right now we glue them along the backbone. And then these discs have holes for your tendons. And that's a tedious process because if you have 3D printed before, you need to take out the resin from each hole, then you need to sit and route your tendon through each of them. And then basically what's happening is at the base, you have 2 motors, one for each side of each tendon, one on the right, one on the left, and you have another one that's actuating a moving base over a linear gear. You can move it inside and out. So most of it is 3D printed because these are very non-standard designs. So it's not very easy to just go and buy a system like this.
So I have 2 questions. So one question is actually on the mechanism for actuating the robot. So I guess in this particular example at the beginning, when it's just making its way through to the left of the first circle, it would bend right. Because I'm guessing you can only apply a 1 torque at any moment in time, right?
Yeah.
So I guess once it gets past the first circle and it wants to bend to the left, then it would apply a different torque.
Yeah.
Okay, I see.
Yeah. So basically by controlling the length of this tendon, so that's what the motor does, reduces the tendon, so it pulls it, so it bends to the right.
Right.
Or the other one pulls it and bends to the left.
Yeah.
So basically you have to find what is this torques, I guess, sequence of torques you need to apply to make it navigate this.
Right. But I guess you're counting on the first circle to kind of hold it in place while you apply the torque the other way.
So right now, assume these are fixed obstacles. So the first obstacle is there to support the robot.
Yeah.
But eventually, something that people have been looking into is using these for navigating like a sensitive environment where there's a lot of rubble or something.
Yeah, tissue, I guess. Yeah.
Yeah. So then potentially, yes, you have to worry a lot about friction, how are these obstacles moving, etc., etc.
So that leads nicely into my second question. So what are the applications so far? Like what are the kind of, I think surgical robotics is probably, it sounds like that's maybe one of the main application. Anything else besides that?
So surgical robotics is very common. I think a lot of catheters also fall in this. You have these different designs to perform different tasks. For industrial inspection, they have been used. For example, Rolls-Royce has a collaboration with a university in Nottingham. Basically, they use these robots to go in a turbine blade or like an engine or like a blade to go in and then perform like board blending tasks or inspection tasks. There's also another class of like these soft robots. So the ones you see on top, these basically have been used to like burrow into soil because they can just go in and see around. They've also been used for archaeological inspection because you can basically you end up not damaging the environment because they're soft. So if you have these delicate parts, you can use them to first go look around and come back, and then you can have a better plan of what's inside before you start digging in. Another thing that I've seen is fruit picking because they're soft, right? So you can kind of gently go, go in and remove the fruit. But yes.
Okay, thank you.
Off the top
I
of my
guess
head.
you need to enforce some sort of a constraint on the contact forces in many of these
For
applications.
fruit picking, yes,
Well,
definitely.
even surgeries, like.
Search,
you don't wanna
oh, definitely.
exert too much force.
There's a whole lot of work on so because they can be used as proprioceptive sensors. So basically, because they're flexible, they're going to respond to the magnet. They're going to bend proportionally to the amount of force that's applied. So you can use this to somewhat estimate what is the magnitude and direction of this force. And when it starts exceeding a certain amount, you start alert your surgeon and saying, hey, like,
Yeah, but like
an
even during
adaptation.
planning, maybe that's another